Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, we got no problem. Have you ever had a collision with something and it hurt? I'll bet you know how this happened. I was once riding my bicycle. A guy ran a red light. He hit me. My bike went underneath his car. I got hurt. He did not. His car barely got hurt. What's going on with that? That's the introduction to the topic today we want to talk about is something called energy. Or energy versus work. In the last video we talked about work, but energy and work are similar. It leads us to a very important definition. This one. Kinetic energy. Now kinetic energy is the energy of an object in motion. And maybe you've heard this from a lot of sciencey stuff. It's energy of motion. So something is moving, it has energy. Anything that's moving. Me moving on my bicycle, that's moving. The car moving has energy. But you know something is going on when there's a collision. We'll talk more about collisions a little bit later, but they're sort of inherently thing. I don't weigh a lot compared to a car, so I lost, right? So let's derive the equation for motion. Now let's review some things that we've learned about in the past. If you recall, there's an equation that V final squared, right, plus V initial squared, one of the equations that we learned about, is equal to 2AD. Now we also know that force is equal to mass times acceleration. But you see A and A, so we can say A is equal to F over M. Are you kind of catching what's going on? So I can then say VF squared plus V initial squared equals 2 times F over M times D. Now watch what I do, people. If I then take this side, I multiply it by M over 2. Watch. M over 2. All right, what happens is the M's cancel. You seeing this? Are you getting this? Right? And where's the D goes? And we know that force is equal to, we know that work is equal to force times distance. All right, and work is energy, right? Or the kinetic energy, right? So we can now plug F times D, right? That equals W. All right, you're going to see this. And the 2's, by the way, canceled. So I can say work is equal to, actually I'll put it on this side. I'm going to take this and put it over here. You can say 1/2 times M, 1/2 times M, times V final squared minus V initial squared. All right. Sometimes this is the change in the velocity. We say that, and then I say work, we can say kinetic energy is equal to 1/2 M delta V squared, the change in the velocity. And that is the main equation for work. Sometimes we need to use this one because that's going to be helpful if we've got an initial and final. But this is the master equation for energy. And if you think about this for a moment, when I got hit by the car, the mass of me versus the mass of the car matters. It matters a lot. And so I have less energy because I weigh a lot less than a car. So that matters, right? Okay. So let's do our example number 1. We have a 3,900 kilogram truck. All right, so we got a truck. And it weighs 39. I got hit by a truck, by the way, like a van thing. And it weighs 3,900 kilogram, and it's moving at 6 meters per second. How much energy does it have? Kinetic energy. Well, we simply will just say 1/2 times 3,900 times 6.0 squared. When you multiply that out, you get 70,000 joules. But here's an interesting question, which is here in the paper. What if the kinetic energy jumps to 12? 1/2 times 3,900 times 12 squared. Now watch what happens. You get 280,000 joules. Now notice this. I double the speed and I don't go up to 140, I go up to 280. I go up by a factor of 4 because it's the square. So it's going to really make a difference if you're going faster. This is why, in a collision in a car, if you double your speed, the amount of energy at the impact when you hit something will be 4 times greater because of the square of the velocity. That's why excessive speeds are very, very dangerous in vehicle types of collisions. So the speed makes a huge, huge difference. So what's the connection between work done and kinetic energy? We talked about work, kinetic energy. What's the connection? Kinetic energy versus work. So the work done is equal to the kinetic energy. There's another kind of energy, right? Or actually, which is not kinetic energy, the change in the kinetic energy. Okay, so this is a key thing. They're both going to have units of joules, right? Joules is how we measure energy and how we measure work. This leads us to what we call the work-energy theorem. And that is quite simply, is the total work done on something, is this the change, remember delta is the symbol for change, in the kinetic energy of an object. Or you could say equals 1/2 times m times v final squared minus v initial squared. So let's do a problem with this, right? So how much work is required for a 74 kilogram sprinter? So we've got a dude who's very fast, or dudette, right? And they weigh 74 kilograms. And they're going to accelerate from rest to 2.2 meters per second. All right? Now, if you think about this, rest, initial velocity 0, final velocity. So we can just use the 1/2 mv squared. So the kinetic energy of this cat here is 74, or 1/2 m, and then v times 2.2 squared. Pretty simple math. Multiply it all out, and you get 179 joules. All right? Super simple. Well, let's do a couple more examples. We have students lifting a 4.1 kilogram box. So this weighs 4.1 kilograms. And he's lifting it, right, up vertically with an upward force of 53 newtons. So picking something up, right? The distance of the lift is 1.6 meters. So it lifts it up 1.60. So this is in the y direction. We haven't seen one of those, right? What's the work done by the student? All right, so by the student, it's going to be work is force times distance, which is going to be just simply 53 times 1.6, which is 84.8 joules. That's question A, if you will. What's the work done by gravity? So gravity, right, that's the force down. This is force equals mg. So we got to find what that is. The mass of this is 41 times 9.8. I need to know that. And that's going to be 40.2 newtons. And the question is, what's the final speed of the box? Actually, the work done by gravity, he doesn't. I guess you would times this by 1.6, right? It's the change in force is what I would do. So to do work equals force times distance, you'd times this by 1.6. And 40.2 times 1.6. And that is 64 joules. But this is 64 joules, if you will, negative, because it's going in the opposite direction. All right, so what we're going to do, if we want to find out now what is the total acceleration of the box, we're going to do the difference. So 84 minus 64, we'll simply round that. That's 20 joules. So the last question it asks is, what's the velocity? How fast is it going? And of course, you just plug this in. You'd say 20 joules is equal to 1/2 times 4.1 times v squared divide both sides by this side, then take the square root. I won't go on all the details, and you get V to be equal to 4.7 meters per second. So a little square root stuff you'll have to do on the calculator. All right, last one. Objects with initial speed problems. So in this problem, we got a boy who is pulling a red wagon, or whatever wagon. And he's pulling this wagon, and he does 19 joules of work. All right, we know the energy, right? And the wagon weighs 6.4 kilograms. We know that. And he pulls at a distance of 2 meters. If the initial speed, by the way, he's got initial speed, so V initial is 0.5 meters per second. What is his final speed? So this is a little bit trickier. So we know all these answers, but we're going to say kinetic energy is equal to 1/2 m. Now this is when we're going to use V final squared minus V initial squared, right? So we're just going to plug this in, and we're going to attempt to solve for the final velocity. So we know kinetic energy is 19, so 19 is equal to, I'm going to say 0.5, so that's easier than my calculator, times m, times 6.4, times V final, which I don't know. All right. So it's going to be, what is it, 0.5? No, V final, I don't know. VF squared minus 0.5 squared. I'm not going to do all the math here, but I think you have the mathematical characteristics. That's how you set this up. When you do all the math to find the V final, and you have to do some square roots in the whole ball game, you get 2.5 meters per second. If you need help on how to do that math, I'm glad to show you that in class. Hey Houston, we got no problems. Energy. Energy's cool. Kinetic energy's even cooler. Because you can move! Houston, we don't have a problem. We'll see you in class.